Okay. Problem two. An accelerated frame of reference problem says a camera is set up inside a truck trailer, bolted to the floor, so the camera's not going to go anywhere. So that an outside observer, so maybe this truck has like a glass side on it, so people outside can see in. An outside observer can analyze the motion within the trailer. Oh no! What am I saying? They're going to look at the feed from the camera. That's how that's. Anyway, whatever. A 5 kilogram block attached to a spring scale. Yeah, see that's a spring scale. Rests on the frictionless horizontal bottom surface of the trailer. Spring scale is also attached to the front. See, this is, dang it, my diagram got screwed. This is attached. See, the string attaches to the front of the trailer. All right. There we go. Now, when the trailer accelerates compared to the ground, so this whole thing, right, we're going to accelerate forward to the right. All right. How would a person standing on the ground outside draw the force diagram for the block? How would a person watching a film of inside the trailer who doesn't realize the block is accelerating draw the force diagram, right? How are they different? So you say, well, a person from outside, if they're like watching through this glass side wall, right, they would see that the trailer is accelerating to the right. Yeah. And so, you know what? I'm going to go ahead and write right on this. Okay. They're going to say that trailer is accelerating to the right. And so when they go to do a force diagram for that block, this person on the outside watching the truck go by is going to say, look, that block inside, it is accelerating to the right. There's a tension force here that's pulling on it, right? And so I'm going to see that spring scale read more and more and more, right? Okay, and that's going to make sense to me, right? I have gravity and normal, right? And you say, yeah, these forces are going to balance. And you say, hey, I have this unbalanced force pulling to the right, and that makes sense because I need that block to accelerate, okay? Oh, look, it's a frictionless bottom of the trailer. That's why there's no friction. So this tension force is what's needed to accelerate that block, and I can read it off the scale as it goes whipping by, and I say, okay, yeah, that makes sense. That T is equal to the mass of the block times the acceleration of the system, okay? All right, good. This is from the outside observer, or I don't know, the ground-based observer. I don't know whatever you want to call it. The person who's watching the trailer accelerate past. Okay. On the other hand, a person who's watching it on the film. How would a person watching the film of inside the trailer? In this camera, they don't see the outside. They just see, suddenly they'll notice the spring scale reading going up, or not going up, but going to some value, right? And so the spring scale doesn't read zero. And they're like, what? Why do I have this tension force there? And a person who's just watching the film doesn't realize that that the whole system here is accelerating. They're just looking inside the truck and they just see, hey, look, suddenly this tension is going up. They would think that somebody was pulling a trick on them and was yanking on the other side of this block. And they'd have to invent some kind of a force to explain why there's a tension there if this thing isn't accelerating, they think, right? And so they have to say, okay, well, just like this is balancing this, so we're not accelerating in the y, I would need this tension to be balanced by some other force here, all right? And you say, I've added on this force on the diagram. To make it make sense, in this frame of reference, this point of view, it appears to not be accelerating. That's because our point of view, this camera is accelerating, right? So this is from an accelerated frame of reference. It's what we call a non-inertial reference frame. So I have to invent a force to explain what's going on from this point of view. This is a frame from a point of view that's sitting still, that's not accelerating. There's a person outside watching the truck roll by, accelerate by. This is a not accelerating point of view. It's an inertial reference frame. In this, Newton's laws make sense. F equals ma. I know it's accelerating to the right. This tension provides the acceleration needed, right? F equals ma. T equals ma. In this one, I have this tension, but from this point of view, it's not accelerating, so I have to invent this. This force, how big does this force have to be? Big enough to balance out this guy. And this guy is equal to, force is equal to the mass of the system times the acceleration, right? You would agree? This T is going to be ma, right? Where this A is this A, the acceleration of the reference frame. So this force that we invent we call it a fictitious force. You say, how big is that fictitious force? Well, it has to balance out that t, doesn't it? So it'll be equal to the mass of the object times the acceleration of the reference frame, right? Okay, this point of view is accelerating at, but it's going to be in the opposite direction of that acceleration. You see what I mean? So, I mean, do I need to put a negative? I just want to emphasize that it's opposite the direction of the acceleration. So I'm just going to put a negative there to emphasize that point. All right, moving onward. If the scale reads 0 when the trailer's at rest, determine the acceleration of the trailer when the scale reads 18 newtons. It's a 5 kilogram block. So you're like, oh, well, the scale, T is ma. You would just say, okay, if this reads 18 newtons and the mass is 5, then the acceleration, you say it's going to be 18/5. That'll be 3 3/5, also known as 3.6 meters per second squared would be the acceleration. What does the spring scale read when the trailer moves at constant speed? Well, if you're moving at constant speed, then in this frame of reference, you say, well, there'd be no tension then, right? Because I need to have a total acceleration of 0 if we're going at constant speed, so I have to have a total force of 0. There'd be no tension necessary. Okay, once it gets moving the same speed as the trailer, once we've accelerated up, and if we're going at constant speed, I don't need a force on that anymore. The tension will be 0. All right, once we've reached constant speed. I don't know why I wrote out the word 0. That's really weird. All right. All righty, there we go. Okay, that's it for problem 2.